Can you hear me?
Yes, I can hear you. You can
Okay, I
proceed.
had a problem with my internet. Okay, you can see now my screen again, right?
Yes, please.
Okay, so I will start to do my presentation. Well, my talk. Is okay?
Yes, you can start now, please.
Okay, yeah. Well, I'm Alberto Maldonado. So first of all, thank you so much for being here and try to speak a little about the thing we are doing in IBM Quantum and focus on Qiskit in the topic about quantum computing. So yeah, my role in IBM Quantum is about the quantum computational scientist. So first of all, uh, we are talking about what is the mission for IBM Quantum to do. Yeah, or what's the goal about that one? So for first one, we are trying to use the quantum computing try to bring the useful things in the world for different characteristics where we are doing and try to look what is the advantage utility the goals we can using with this kind of new technologies in a novel things using yeah this kind of different paradigm in a complex uses cases. So for what is the reason about that one? Well, we know exists certain problem we need to use or solve it with the using a computer or even a problems you are using a high performance computing, but we all still have certain problems with that one. Actually, we had certain proposals using AI or we're using right now with this new paradigm try to solve these complexity problems in an easy way. So that is using the quantum computing. What is the reason about that one? Well, exists a certain things where we are using in a classical computing a complexity time in exponential way. We take a lot of problems like we call it in the hard problems or MP. That means like no polynomial time try to solve it. And in a quantum we can in certain problems of that one use it try to reduce the complexity time in a polynomial time. So, what kind of problems we can try to do, or what is the benefit try to solve it in a quantum computer? Well, we're using the properties for the quantum computer and try to transfer in a benefit. And that means it's like focusing particles or molecules, try to identify the properties for a certain simulation parts, and we are trying to solve it. That one. So, the first thing we are trying to do is like identify what kind of problems we can do it and a limitation and try to facilitate in a quantum computer. And that means is like how we can translate information classically, we can recreate all in zeros in one and try to transform in different aspects to solve it in a in a quantum computer is not necessary because we're talking with the same atoms, electrons, neutral atoms, or whatever we are talking to working and specific doing this characteristic in a specific models. So that is one thing. And what is the benefit of the solution of this one? Well, other things we'll try to create is identify the benefits to save certain energy, facilitates the make decision for accomplish things like what is the Beckley rotten problem, the Naxa problem, or discover a new molecules or antibiotics. Like in the case of the COVID time, it was interesting try to solve what is the best machine or the best characteristics to solve that specific new yeah situation for the medical thing. So even that one or even the characteristic we're working during the hardware, we can solve this one in a specific new technologies and identify the sensing part for different tools or different characteristics in a medical, in an industry or different characteristics. So follow with this idea is like the interesting thing about the quantum computing is identify we're working in a certain specific new space, what is the Hilbert space, and we want to recreate this one with different characteristics. The simple way we are thinking about that one is like in the classical way we're in a group where we are only two operators, the add or the multiplication we're calling or and and we try to create in this logical way all these mathematics we are doing right now in a quantum computing is different because we are in a specific space. So with that one, we can recreate all these characteristics in a specific patterns, and we can identify what is the benefit about that one. The first one is like the molecules is the same. The characteristics for a specific graph we can create in a qubit. It could be one node of a specific graph, and the interconnection of this one is the Hamiltonian we can recreate and try to obtain the minimize for the energy we can obtain the solution about that specific problem. So the previous information of the previous problem we can do we can try to think a different way what is the solution about that one. So follow with this idea using the algebra to identify what is the benefit of this one is the detection, the vehicle problem, improves different things, and identify even what is the risk to identify for a future decisions, like the forecasting things, optimization problem, innovate different detection for the characteristic information we got it because the the cameras, the sensors of this one are using the quantum mechanics properties where we're doing to digitalize to obtain this analogic information and trying to transform in a classical computer and they try to understand in that one. So in quantum computing, that is not necessary because we're working in the same theoretical part, or we can detect of this information in other characteristics is beneficial for us. So, quantum computing is a really good tool because we can recreate all of this information, not to recreate everything in zeros and ones. It's like we can recreate all of this information in a specific same space and recreate all of this information using the same characteristics and try to reduce this step. And with the quantum computing, the complexity time we can to record all this information is getting in the same space. So that is a really cool tool, and we try to do that one in these specific problems. So we need to think the nature is quantum. The things we are trying to do or try to solve right now in the nature, in the space, whatever we try to solve, we need to understand we need this a lot of high performance computing or try to use a quantum computing because if we can try to simulate everything in in a classical computing, what is an atom, what is a molecule, what is a specific problem we need to create translated in zeros and one. But what happened we are trying to use in a qubit because qubits is a particle. So we need to create all of this information in a specific particle and try to solve everything about that one. And the benefit of that one we can recreate and using the same properties for quantum mechanics. So follow with that one, we are trying to do understand that is the problem, what is the limitation we got in a classical thing, and thinking in a quantum structure and a quantum processing, identify how we can optimize that problem in a benefit for a time and a number of the information and money of the resource and try to see what is the benefit about that one. It could be in everything aspect or in a specific aspect. So that is interesting thing about quantum computer is not just working with zeros and one and try to do a specific things. We can use other properties or try to recreate in another way where we are understand in a quantum mechanics topic. So, following with that one, what we're doing in IBM Quantum? Well, we are trying to identify since previous 2023 what is the benefit to use the hardware. In IBM Quantum, right now in IBM Cloud, we have this platform where we are connected with a lot of different hardware. We had at least 127 qubits, and we try to recreate what is the benefit with this specific hardware and the benefits for try to solve a specific solution for the classical use case we got it right now. So in 2023, we find a specific problem. We try to recreate this complexity in a classical, and we got tried this solution. So after that one, we try to do more focus in the benefit, like exist the hardware, where what is the characteristics we can limited it, how we can optimize that information try to mitigate the error, try to do the correction, and try to do the benefit for the hardware and identify the use case we can do it. So the next step we try to do is correct the information about that one. So the benefit of this one is like, or we had a lot of hardware and try to do a lot of qubits, so we need to understand more about the hardware we are working, try to mitigate it, and try to do the correction about that one, and try to see what is the benefit for for multiple use cases we have right now. Try to solve in IBM Quantum or yeah, in different aspects, and simulation, optimization, chemistry, and machine learning process something. So, what is the quantum advantage? So, we'll try to identify. We can reduce about the classical part, the time, the resource, or both, or even it doesn't matter what is the topic. We can try to do in the classical or specific use case the information we got it, and we try to transfer in a quantum computing problem. That means translating a quantum circuit using that specific hardware, try to do the post-processing to mitigate it or try to do certain techniques to do the correction for that information, and try to establish this kind of output even when we're using a noise quantum devices. We obtain a specific rule results and we can do in a confident way we are doing the solution this we expect for that specific use case. So right now we are just not focusing on trying to solve one specific problem, is understand the physical or the physics things about that one, try to do the physical part for the hardware, try to understand what is the limitation about the hardware, try to solve this software thing, and try to understand the hardware to reduce the noise, try to optimize the information, and when we obtain a specific solution, we say that that solution is a good one compared with the classical computers we are doing. So, what is a quantum computer? So, previous of that one, we need to think in exist different properties about quantum computer. But why try to do or why need to use a quantum computer? Well, we are using the microchips when we are trying to do even reduce the number of the transistors for many years. But what happened when we are trying to do small, more small, more small? Well, that is part of the Moore's law. When we are trying to do in a certain moment, we are trying to do or we try to working in the quantum topic area. So our benefit of this one is try to instead of waiting for that one, why not to use right now and try to build this quantum computer and try to use the properties and benefits of that one. And the three properties we are very interested is the superposition, the entanglement, and the interference. What is the benefit of the superposition? It's like flick a coin. When it's flipped in the air, we can see two different characteristics: the tails, the head, tails, and head. So in this case, we translate in a quantum computing is 0 and 1. 0 and 1. Imagine you can integrate these different coins in the air and try to do certain connection, and depends on the value of this one, we can do certain interaction between all of them in 2, 3, or all of them. So that could be the entanglement way we can do it. And what is information on how to do the measurement is when the cone is in the table in our hands and sees tail or heads, and we need to count the solutions. And depends on this way we obtain a certain probability distribution obtain the information about that one. So, with this information, we can obtain the solution for complexity problems and try to reduce the information. Because in this case, compared with the classical part, we need to do a for, like do the selection, what is the state, what is the next one, what follow with the next one, and so on. So in this case, we just need to use 0, 1, try to do the superposition, it could be both in a same probability. But we need to increase the probability for the task or those specific states. We need to identify as a good solution. So in the other way, we can do the interference when we have a certainty solution and doing with these properties increase the probability the states we want to do that one. So that could be the one way we are doing quantum computing. So the benefit of this one is like with these properties we reduce the information, or we need to explore the geometry of this information following with these characteristics. So, consider previously with a classical computer where all you say is working in a binary way, zeros and one, and try to recreate the information. What happens when we're working with a specific length of information? We can recreate a chart, a string, a float, an integer value. But it depends on the characteristic for a quantum computer is necessary about that one because we can work with the angles, with the model, with the amplitude, and the base of this information we can connect with this one, or even we can obtain 0 and 1 with a certain probability of this different state when we are working with multiple qubits. And comparing the same one, the classical bits, we are using the classical logic circuits when we are working with this specific gate operation when we recreate this different interaction like other, like subtract, multiplication, logical operation, or depends of this when we can record all the information we need to do for multiple and complex calculation. So yeah, in quantum computing we're working with a block sphere, the basically thing when we are in the up the zero and the down one. And the depends of the one depends of the position we are more close. If it's more close to the up, it's close the probability to obtain 0. If it's more down, it's probability to obtain 1. And the base of this one is the characteristics about the quantum gates is kind of similar, like the logical part or the classical part. But the interesting thing is like we can rotate information for like this block sphere, and the sphere is always the same radius is equal to one. So the probability depends of this value is depends on the amplitudes model. And this information we can recreate in different or similar information of this probability. Like and where in the halt we had probability the half probability to obtain 0 and the half probability to be 1, but we have multiple infinity values to obtain the same probability, but the geometry will be at different meanings. So what is the thing about working with multiple or the characteristics for the geometry? Because we don't need to translate just in 0 or 1 or half a half. Because depends on the information we can get during this multiplication or this operation, we can obtain information necessary to do or transform our specific problem. So depends of this one, we can obtain multiple states working in integer values, negative, positive, complexity values or imaginary values. So depends of this possibility information, we can create a complex state. And the complex state is working in quantum mechanics. And that quantum mechanics is working in a Hamiltonian. And the Hamiltonian, we can do a specific geometry in the X, Y, and Z or the identity values. And the best of this one, we can create all these quantum mechanics properties using in our hardware or try to program it, this information work in this bits information and try to translate that information using the quantum gates. So depends of this information we got it, depends on the probability we can try to do after the measurement if or is 0 or is 1. 0 or 1. So when we do it or apply that information, we need to do a specific operation. We will lose this like a particle, no, how can I say, like wave properties when we had certain probabilities and we move in a particle where we identify a specific value is 0 or 1, 0 and 1, but this is associated with one a certain probability and multiply well, that probability we can obtain when we multiply or obtain the model for this complex value or for this amplitude for this specific qubit, the information about that one. So even we can start or put the condition of this one in different way. We can start this one in 100% in 0 when we can finish like 50-50 or 82 or 40-60% of all of this one. But what is the meaning about that one? Well, that is a part like us, like scientists, developers about quantum computing, understand what is the probability about this one information or the probability distribution about all multiple states or the value for the specific state, what is the most with high performance probability, and we can translate our decisions. So for that one, or the summary about that previous introduction about that one, we can illustrate here. We have a specific state. We do a specific gate when we translate the information. We started always in zero, like in classical computing. How we can translate one variable, we can start with a zero value and we select or we can initialize with a specific value. How can we do it in a binary way? Well, we select a specific gate and we can transform the information for that value. We can start with one, well, we apply specific gate calling X gate, or we are doing a rotation X in this specific qubit and try to transform the initial state to zero to 180 degrees, and we can translate the information in the state one. So basically, we can translate the information for one qubit, and we obtain started with 100% in the state zero and a 100% in the state one. So the interesting thing is like what happened? We are starting with another specific gate. It doesn't matter to do a specific 180 80 degrees of the angles. So we try to do in a half. What happened? We're doing just 90% of this rotation. Well, that is the Hadamard gate when we are trying to start with the state zero in a 100%, and the output will be the half. Is 1 over the square root of 2 to the 0 and 100 state 2 to the 1. Just a reminder, this kind of properties of this notation is the bracket notation. When we try to simulate units, is a vector to size two dimensions, and this is like a column, 1, 0, and this is 0, 1. So we can transfer this one in a specific vector to transfer this information. So this one is not necessarily a probability distribution, but what happened to apply the model? So 1 power 2 is equal to 1, and square root of 2 power 2 is equal to 2. So we have 1 half and 1 half. And the probability to obtain depends of this one. Well, we need to do multiple number of the shots. And we increase the number of the shots, we associated almost the same probability, 50-50%. But theoretically, we can obtain the same probability. So we can simulate this one in a real condition, or we can write this one in the theoretical part obtain the same probability, and we can do the experiment and we obtain the same information. So about that thing, we can try to do the superposition. It was the same probability. So we need to remark that information with this slide, just to remark what is the benefit of doing the superposition. Well, just reminding zero state, one state. We had a basis. What is this one? When we try to do POW, is a linear combination. And a linear combination, we can recreate any point of this specific space. What is this space? The Hilbert space is a complexity space in dimension 2. So we can just add of this one a scalar, we call it alpha, and other scalar here we can call it beta, or we can see in this case. So when we try to put that information, we can say the get 0, get 1 associate with this computational basis, and we can associate the probability of this one. When we put the 100% in the state 0 is equal to 1 here, is just the state of ket 0. And we have another case, 100 here, or state equal to 1, is the ket 1. So we can recreate the depends of this, can just check the probabilities when we apply the model, or just to find a different properties or that specific block sphere where is, yeah, the norm is equal to 1, and we can translate the norm is equal to probability, so 1 is equal to 100%. So we obtain this all information and just to recreate any point of this space. So the superposition is like we can recreate the flip coin, associate the alpha for a probability to obtain heads, and the beta to associate the obtain the tails. Head, tails, head, tails. So we increase or reduce the probability depends of this one. So, Colin, with this interaction more clearly about how we obtain the probability this one is like alpha and beta, we obtain a certain probability associated with this one. Always we do is equal to 1. Why? Because that the probability of this space is like is a normal space, so always the model will must be equal to 1. If one happen more or less, we are doing a certain different thing or we are lost certain information. So the interesting thing we need to be important is alpha and beta. It could be a complex number. So remember, we need to use that integer, um, positive part, a real, and then positive or negative in a imaginary part. So we need to multiply with the complex conjugate value of this one to obtain the probability, and we can try to do that one. We obtain equals to 1. So, just to make more clear about the superposition is important when we are trying to do the working with the quantum computing. And why? Because when we are starting, we can try to always start in zero, but depends on the case, we can move in multiple states. So we are trying to work with the block sphere, where is the best user working when we are trying to use with one qubit, and we can identify the properties in the different axes. In the interesting thing, we are always focused in the axis C, because in that one is the zero, in the up, in the down is equal to 1. So depends of this value, we can identify what is the property, what is the values, and we can identify depends of the axis. In the y is more the complexity value, so exists a certain relation with between the c and the x basis, and we can identify what could be the position of this one and the characteristics of the information. What happens when we have information in the right? Well, no, here in the part of the, yeah, in the behind or in the front of the state. It's kind of similar, but that make different because here it will be the positive part and here will be the negative part. So depends on this information, we can identify what is the position of our state, and depends on the problem we try to solve it, we identify is a good or bad interaction or try to do another way to solve the problem we got it. So depends on that one, depends on the geometry. It doesn't matter because when we multiply it with one specific value, we can obtain a certain probability. Like this one. What is the probability for the state square root 2 divided by 2 in both cases? So when we do the value, what is just a real value is when we try to use, you need to do over 2 power to 2, sorry. So is this result is 2 and here is 4. 2 and 4. So 2 divided by 4 is equal a half. Half plus a half is equal to 1. So we got it, same probability. But what happened when we're doing an imaginary time or imaginary value, sorry. So in this case, we are multiplying for the power of 2 is equal to 3 and equal to 4. So it's 75% the state 0. What happened here? Is a negative value, but exists a probability negative. We need to take a look about that one. So the conjugate negative value here, we need to multiply for the inverse. So if it's negative, we multiply for a positive value of this one. So negative for multiply both positive is negative. But what is the power of 2 for I if imaginary? This is the value of square root of minus 1. So power of 2 for the square root of minus 1 is equal to minus 1. So negative for the minus 1 is positive. So we had 1 over 4. What is the 25% of the state 1? So always the probability, even if we had a complete value or positive value, we obtain the summatory of all the states equals to 1. Continue with this one, and we'll try to do what is the entanglement thing, where is kind of interesting way we try to do here is like we had this specific quantum circuit for a real hardware, we got it previously in Navian Quantum, and we try to recreate all of these characteristics in a specific quantum circuit. Where we try to do is like how can connect the information here of this one and try to do the entanglement way. Well, when we try to do in a classical way, is just add or concatenate information. But what happened? We got a certain specific probability distribution. Well, we need to divide the information of this one and the summatory all of this one is equal to 1. So when we had two qubits, it's obtain the probability for all the state we got it and associated with another scalar value. And of this one, the summatory of this one will be equals to 1. But what is the difference to do is entanglement or no is entanglement? Well, for this specific example, we are just looking for two qubit gates and we try to associate a certain information. And you see, in this case, remember when we try to do the superposition, this is the half and this is the half. Because it could be is when we do the model, this will be 2 and this will be 4, so it's a half, and this is the other half. So yeah, the symmetry it will be the same. In this case, even it's a negative, when we're doing will be positive because it's minus per minus, minus by minus is equal to 1. So when we try to do that is what is the difference for no entanglement and entanglement states. And you see the difference over here as like we saw what is associated with the information. We can say always one state is equal at one specific value. It doesn't matter the other state, always equals to a specific same value. But what happened here is 0, now is 1, the second qubit is 1 and now is 0, and happen here is 0, 1, 0, 1. So it's different, the both stated. So we don't know how can we try to factorize the information. For the first one, yes, we can separate the 0 and multiply for one specific superposition of this one. But what happened here, we don't know. So we cannot rewrite it in another situation or in a product of two multiples one cubic. So in this case, when we try don't separate of this one in terms on different one qubit information, we call it R entanglement. And that, what is the benefit of this one? Well, it's just a multiple benefits about that one. It's like we can transfer information of this one. We can do integrate information to move 0 to 2. Try to entanglement this information for this one and try to swap the information 0 to 1. So the information for 1 now will be the information for 0, and we try to do the operation of the information for the state 2. So this can be different interesting things. Try to do certain communication information between two different qubits and try to connect that information with these two qubit gates and create a state we don't exist in a classical computer. Or what is the benefit of this one? Even increase the possibility to obtain this complexity solution in a specific problem. So we need to just reminder in a quantum computer is important works with gates. In the quantum circuit, we call it the quantum gate to transfer the information in a quantum state. So the gates we're using in a classical, we have the AND, the OR, the NOT, the NAND, and the XOR. But here we're using one cubic gates and two cubic gates and the measurements. The first one cubic gates we try to do specific rotation for when we saw previously for one. And what happened here? We had another two cubic gates. What happened here? What is interesting about that one? Well, the interesting of this one is like we try to put the incarnation for the entanglement. If you try to see this specific circuit, we can try to translate the information. Like I told before, for a specific, we start with one specific state in the qubit 0 and one specific state for qubit 1. We call it T0 and T1. We rewrite it, and right now, with this quantum circuit, we're doing a swap. Now, in qubit Q0, we had information for C1, and the qubit 1, we had information for C0. What is the thing about that one is like we try to recreate for specific hardware how can we all connected because one limitation you use often this specific hardware is like all not all the qubits are connected. So using that specific part of the quantum circuit, we can connect certain information we don't get it. How many in that case we need to do for 5 to 12? Well, we can translate 5 to 6, 6 to 7, 7 to 8, and we got it, the connection. So we have one, two, three SWAT gates in this specific part of the quantum circuit and try to translate that information. So when we try to do multiple qubits and we try to recreate that interaction, because in the simulation we can connect everything is are interconnected with all of them. But what happens when we're doing a hardware? Well, we need to think what is the different possibilities we try to do the other one. So the other thing we try to do with the one qubit gates and try to do with this connection is like the entanglement try to do certain connection and certain condition. The two qubit gates, for example, we do a condition depends on this value we call it a qubit gate and the target qubit gate. So when we try to do the target, is change the value. In this way, this is the symbol uh, for the addition for like similarly like XOR. So in this case is when is both at the same state we do it we put is equal to 0. One is different is equal to 1. So in this case, 1 is 0, we can move it in 1. Is 1 is equal 0, and when we don't add it, and is 0 is equal to 0, so it doesn't that's the change. But in this case, it's more like a condition, like a programming part when we're doing this conditional like if. What happens when if is equal to 0, we don't have nothing in this specific target. When the control gate is equal to 1, we move it this target in a negative value. So it's like the control signal gate because depends of the control value we can apply the negation or no. So in this case we can do a specific encoding information depends of this value that to do this specific multiple gates and try to do other decoding information and try to optimize or keeps the information or identify of this encoding, reduce the information or try to recreate multiple states and obtain a high probability of the states are interesting for us. Why is this necessary? Well, it's part of the program when we are develop the quantum circuit. The quantum computing is essentially the quantum mechanics. We try to do the interference information because we try to do this one is increase or decrease the information we try to do in a specific state. So when we got it, the same probability of the state, and we're interested in one because we know that the state is the solution for us what we want the same probability or increase the probability and decrease the probability of the other state because remember the all the summatory for all the probabilities is equal to 1. So with the interference, we had the black sphere. We call it it's positive, negative, complex, imaginary, real. So what happened with the probability with that one specific case, we can just separate the information for no interested for interesting thing. And we try to do in that specific case is just put one in a negative value. So that negative is like all the negative value are the state of interest. How can do decide what is the positive, what is the negative? Well, we design the condition, the oracle to identify in a specific problem what we want to do. And with these interference things, we can do a specific kind of reflection when we try to augment the probability for the state of interest for us and in that specific problem. Because the other, it doesn't matter, it's not for our interest. So we will try to do that one, we can increase the probability for them. So with this kind of interesting things about quantum computing right now, we're working in the quantum computing is like using the probabilities to amend or increase the probability for the state of interest. But what happened? We're trying to do, I think, more a simulation using the nature for the quantum mechanics. We can translate in a simulation for molecules or create a certain chemical reactions. So about this one, we try to do different processing and we try to solve it a complex molecules and try to identify what is the minimum energy that they excited or no for that specific molecules. Identify is a good or bad decision. Well, for that one, we just need to remark in a classical computer spend a lot of time just to represent the energy configuration about this one. Just this the information is just a little complicated, so we need to identify and try to optimize use vectorization, GPUs, TPUs, whatever you've done, or even FPGA, try to reduce the information used to compute this one. So it's a really big challenge. Even we can call it well, we know what is the characteristic of this one, but what happens we try to do it with a more complex molecule or information we don't know what is the properties or what is the advantage to do with this particular a molecule and try to see in another way. So we cannot do it. We need to spend a lot of time and spend a lot of techniques or spend a lot of computational resource in a classical computer just to identify about this one. So, how can do in a quantum computing? Well, in IBM Quantum, we try to do like we can recreate this one in just using 160 logical qubits. This is not like the real qubits we had in the computer. These logical qubits is another proposition we can decide when we're working with this qubit will be the good one in the moment. So that will we do a good connection with all of them, so you always need, in a moment, we try to do that part of solution, and we can reduce the resource, the exponential time to spend in this kind of particular specific, and try to explore new ways to use in different topics. So right now, how we can do the quantum computer in a new way for us is try to unlock that potential we got it to do the quantum computing to reduce that information, recreate this one in a new, different or multiple ways, try to do the quantum computing. But in this case, it's like we are right now try to do in a different approach that to use right now the classical, the quantum, and we call it hybrid quantum classical approach. But right now, when we try to do this kind of benefits of this post processing or during processing using AI and this kind of procedures, we can obtain certain multiple ways when we try to obtain this quantum computing tolerance to the noise, we can increase the potential to use a quantum computer. So thinking about that one in a new way for the computing. So we have these specific cases we don't know how to do or the internet what is the best solution or what is the result we can try to do it. So when the quantum computer we can unlock that barrier and try to see other possibility to do the same solution or even a specific example for that use case, see what is a good benefit or bad benefit or the limitation we had in the quantum computer, everything is now because this is a novel. And right now we are working and IBM we are doing an amazing job trying to obtain the hardware, the integration, the model with Qiskit programming, and we love try to explore many different ways and try to help in different companies, associate benefits. I try to do multiple problems and see what is the potential for the quantum computing. So at this moment when we are doing all the valuable things to solve this one is like no meanings is like we can try to do or solve all of this one like in a couple of seconds. It doesn't matter the size. No, we try to identify what kind of the problems it is interested, but all the areas is complex for us. And we say, well, this is a specific problem for a use case for a specific topic or area for our interest, and we try to deal deal with the problem with what is the limitation for the hardware, what is the properties, the techniques, and reduce the time of this one or obtain a fidelity good solution comparative with the classical part. For example, if you are doing a performance value or metric about that one and you say, oh yeah, our fidelity to obtain this performance accuracy for one specific decision is the 75%, well, on a quantum computer is 77, well, it could be like, it's not a good progress, but what happened we're doing, oh yeah, that we're using 1 billion of information, well, that is relevant because we are not losing money or we're not losing that spend of the time recreate in a classical computer. We can increase with a quantum computer, even a hybrid way or a full quantum, and increase advantage for many things and many solutions. So we need to think no need a quantum computing for center things like the arithmetic of video games. We can try to recreate some video games about using the quantum computing properties, but more for using in an educational way. That is good. But our interest is like to teach with these video games, try to solve or understand what is the thing when we got in a fault tolerant quantum computer to solve two of our most important algorithms is the short algorithms and the Groves algorithms. The Groves algorithms similarly like the interference example. When we had the same probability for specific things, we don't have that what is the solution. We only know what is the condition to obtain a specific solution following like okay we are selling for an example is like we identify one person who's wearing glasses with a red jacket with a purple shoes, so all of this information we don't know what is the person, we only put certain characteristics. Well, we increase the probability depends on these characteristics and we obtain all of these to uh, fill these kind of characteristics. We say oh increase the probability for them. And what happened with the short algorithms is like it's part of the cryptography. We are working with RSA when we can use this security just using these copyright values with using a big prime value. We can separate into coprimes. Well, the short algorithms try to find this one in a polynomial way. What happened right now with our security? Well, that take exponential time. So the solution right now for the computers, classical computer doing safe or security is try to be the most bigger number price number we got it right now because that takes more time for the other computers and the facility for the hackers or the people try to do is try to identify what kind of the number will be associated for the co-premier and update this case to access to the information for another person. Take certain techniques so take a lot of time. So that is the benefit is secure for us. But with these sort of algorithms, we can reduce that exponential time in a polynomial time. And other interesting example for use case, we are working right now in quantum computers, the chemistry materials, the optimizations and search, machine learning AI, and the numerical simulation. And all of these one are similar because we try to identify a specific in another approach, not necessarily using the same point of view about the classical computer with zeros and one and to recreate this kind of number associated in big numbers. We're more working with the chemistry like recreate a geometry for interaction where entanglement of certain structure or in a graph with the optimization or the information for the machine learning depends we can translate in terms of angles on terms of the amplitude value or the numerical values like recreates all of this one in a graph too, and all this information to obtain the minimal energy to interact in an excited state for chemistry or materials optimization we obtain the minimal energy trying to translate is optimal to identify the minimal number, or we can put the negative is the maximum to increase the probability for the state we find a solution, or the machine learning in this depends of two is a specific value is increased or no, we can put a label, or depends of the value it could be a prediction, for example for the forecasting, and the numerical simulation is more a general way because we can do the finance or the energy. Oh, well, all of this one we can put in different topics. Like we got it, the aerospace, when we had like the aircraft computation fluid dynamics, for example, the automotive, we can auto design and simulate the characteristics of this one or the advanced batteries when we are working in this interesting topic, or the chemical, where we can try to do the isolation product development. Other example for electronics and semiconductors, well, we're working in that part using the quantum computing, or we can find or placement and routine optimization for that one. The energy is always important because like that is part of the materials and the optimization of the final service when we can record everything in terms of, for example, the formula optimization problem or the healthcare and life science. We can identify the property for a specific molecule and or try to propose a new drug discover and try to design or try to optimize what is the limitation about that one. So in IBM, we are working right now in using this procedure using Qiskit. Probably you know, probably you start to know what is Qiskit in this event, and using the IBM Quantus for IBM Cloud. We got it right now. And what is the goal? Try to find the utility scale work. So like we understand programming part, identify how is working the KPUs using the mitigation, the correction, and try to solve this challenge we got it right now in IBM, and we try to solve it. So quantum must be performance, and quantum must be easy to use. So it is not because it's so complicated, must be interesting, it's just a few people. That is the reason we got it here with Qiskit Fall Phase. We try to identify what is the benefit when try to optimize not just for a specific problem, if not for everyone. So the interesting thing we are doing right now in IBM Quantum, we have these different characteristics. Or like the Qiskit function for a premium people, you can access for specific models for different partnerships for different quantum computing partnership we got it right now to solve specific problems for optimization, chemistry simulation, and so on. And we had our service developed for the Qiskit SDK, Qiskit add-ons, Qiskit Transpile service, SQD, for example. If you are in the Qiskit summer school, you're working with one of these add-ons, is the SQD, and we try to recreate this kind of problems and facilitate in our terms using Qiskit. And the other is like Qiskit servers or try to do integration with HPC, so we can even do that one. And the benefit you are trying to do, we had the Qiskit Code Assistant with benefit to try to help us to reduce the time to use the Qiskit version. And the other, when we got all of this information, just we need a quantum computer when we are connecting a cloud and try to identify and redo the connection on this one with a Qiskit runtime. We are trying to do a sample of the information, do a specific probability, or doing the estimator when obtain the specific molecule or the properties in terms of a specific Hamiltonian in terms of X, Y, or zero identity properties, and we can obtain the energy value. And of this one, we can even connect with another characteristic just to do the high performance classical computing. So practically, IBM Quantum, we're working all of these characteristics just to do a benefit. You can work in multiple projects and different multiple areas for solve it, the interested uses case you want to do, and thinking in a quantum computing way. So, Qiskit, as simple, if you need a circuit, please, you need Qiskit. So we know exists multiple ways we can try to work with quantum computing, but right now in Avian Quantum we have, and we try to do even in 2024 for this unitary fund survey or unitary foundation survey, we can Qiskit is one of the most important SDK you can learn about quantum computing. You can start with quantum computing. So even if you want access to the Avian quantum hardware, you need Qiskit. So the benefit of this one is not because we are part of the company, is because we spend less time compared with other ones, even using uh, the same problems and try to synthesize and transplant information. What is that means? It's like we can reduce or optimize if you had a big number of the gates in your quantum circuit, we can reduce how we can try to solve it in a specific hardware, and the time to execute it could be less time to do the procedure for a hardware than using ticket. So in Qiskit, we can try to increase the benefit compared with other and reduce the time, try to work better. And yeah, the quality radio for 2 cubic gauge is really good. It's just to one. In this case, compared with thickness type, because we try to do is like the fidelity for the 2 cubic gauge is the most complicated part we are doing, and our hardware and try to transfer it is try to reduce the not necessary this 2 cubic gauge. For example, the SWAT identify what is the benefit and reduce all of them because not all of them is working good. Yeah, try to do this. The anatomy of the quantum Qiskit is like, yeah, identify the problem, try to optimize the execute of the hardware, try to use him for using the Qiskit runtime. After that one, we got in a specific procedure and we obtain the results. So the things we are doing right now in Navin Quantum and working on the characteristics is we're using Qiskit library when we obtain this information to create the quantum circuit, how we can do the observables or the measurements, obtain information in a sample for the probability distribution of the energy value. For that one, after this procedure, we need to transfer, yeah, transpile or transfer the information for the circuit to create is a circuit. This one is follow the properties for a specific hardware, and that specific hardware try to do this observable and just give that specific information. We move it in this specific hardware. So basically the workflow we're doing when you are programming a quantum computer and you want to use specific hardware is like you have a problem. You think it's important using a quantum computer. You have that specific quantum circuit, and you identify what is the input, what is the output. What you need to identify is the sampler estimator. Well, that one is like, okay, now choose your hardware. What need to do? Transpile because we need to translate the information in a specific basis gate because not all the quantum computers works with the same two qubit gates or the basis gates. We need to recreate all of them in in a simple way because you can take multiple two qubit gates, but we just have a specific just one two qubit gate in the hardware, and we need to recreate all of them in that particular two qubit gate. So we need to optimize all of them, and after that one identify what is the goal, what you need to execute. Sample estimator. This primitive we are working in IBM Quantum is like distribution probability of the energy for a specific Hamiltonian, and that one is just doing this procedure to obtain the information in a visual way in a dictionary that information and visualize what do you want. So this four module is the important thing we need to do. At the moment we need to recreate all of this information, and you need to understand what is the output. So with these add-ons we try to do is multiple ways we can do it in translation and start to do more benefits like AQC tensor and PVF in the section for create more benefits for the quantum circuit. Or the translation depends, it's a big problem. We can try to do the circuit coding or the OBP, sorry. And in the primitives, well, we had the same thing. And when we try to do the sample or the diagonalizing for this information, well, we can try to do the SQD when we obtain a specific post-processing information for the important thing we needed. So, continue with that one. We increase more part, try to unlock the research in quantum. So the thing is like we need the software. You need to understand with the benefit we mentioned before. You apply it in Qiskit to connect with the quantum computer and create a specific work. So yeah, I think you had question at this moment. It could be good. And you had any question, any situation, and then listen me in a 1 hour. It could be complicated. I don't know what you think. It's good, it's bad.
Thank you. Can I ask questions? Can you hear me? Can you hear
Yeah,
me?
yeah, I can hear you.
Okay. Thank you very much for the beautiful presentation and quite explicit and concise. Yeah. I have a number of questions. The first one
Hmm.
is about quantum optimization.
Yeah,
Yeah. In talking about optimization, do you mean the circuit construction? Do you mean optimization in terms of the circuit construction, or do you mean optimization in the sense of what we know in mathematics?
yeah. Quantum optimization, we can call it like take this binary problems. We call it like quantum non-constant binary optimization problems. When we had this like taxa problem, the travel and size problem, the vehicular routine problem, when depends of the situation, we had a specific graphs or specific equation binary information. We don't know what is the optimal solution. For example, you had the NAXA problem when we have this specific capacity for the NAXA, and you have this specific items, what is a specific size of the item, and the value of this one. So we need to identify what is the optimal. When we increase the number of the variables, increase the complexity time, and for consequence takes a lot of time problems, and we can try to turn it in an empty problem because it's exponential time. So try to obtain the information of this one is take more time, and the other problem is like when we try to do is a cubo, so that translates in a slack variable. So increase the number of the problem because we need to be unconstrained. So it's like we have certain capacity is like less equal to one or equal to one is a one condition or one constraint. We need to remove it. For consequence, we need to do the unconstrained binary values. So after that one, increase the problem, more variables, is more difficult. So in this case, with a quantum computer, we can try to translate this one, create different techniques, and try to obtain avoid the slack variable, for example, or try to do even with a slack, try to optimize the probability for a this specific problem compared with a classical computer, and obtain the optimal solution.
Thank you. The second question
Mm-hmm.
is on the circuit diagram you showed us for the encoding and the decoding. I was expecting to see a reversal of the gates. When you showed the circuit for the encoding, I was expecting a reversal of the gates for the decoding, but I think they were different. Yeah.
Well, let me this one, right?
Yes, I think around here. Yes. So I was expecting a reversal of the gates, but I saw that it was not exactly a reverse of the gates.
Mm-hmm.
Okay. So I truly want to see what happens. I mean, how do you determine decoding from encoding? I mean, does it not matter in the type of gate that was used? For example, I can see here that there are three Adama gates.
Mm-hmm.
Also, there are three Adama gates for the decoding, both for encoding and decoding. Okay. But for the other spin that I'm seeing, I cannot see it relate exactly the same way. So I was thinking maybe there could be a similarity in the circuit diagram on both sides.
Oh, okay, yeah. The thing is like, yeah, depends, like you say, depends on the decoding, what is the information we want to translate it. So the question is more like, what is the C value? For example, it's like a specific angle or is a specific one qubit gate. It could be translated in multiple qubit gates, and we are only reducing the C value and try to do the codification of this one. What is the benefit of this codification? It could be more for a quantum error correction, for example, and try to do if it's still working the it's just an example. We can try to codify the information for the C state of this qubit. So we need to do the encode information and try to avoid the error and try to do confirm the information is a part for the decoding and to not be any modification in the gate because if we to modify here, we need to don't modify because they will make create more error things. So this way is a general example, we can try to do this quantum circuit to do a specific problem, but it's not necessarily a specific case. So it's more for a visualization thing, but yeah, it's like a benefit we can try to do at the moment to recreate a quantum computer or a specific state for we call them C.
Okay, thank you. Then the third question is
Mhm,
when you showed us the quantum platform, the IBM quantum platform,
mhm.
I want to ask that from your statistics, which areas do you think are still very much open to research?
Oh, research, multiple
Yes,
cultural research.
yes. I mean, the areas that are still widely open, particularly for mathematicians.
Oh,
Okay,
yeah, yeah.
yeah. So I think you are the center. You can also let us know this. So which would you advise want to go into? I mean, in the current state of the arts. Okay.
Okay, yeah. Actually, the interesting thing about how we can be more involved in these kind of topics uh, is a really good question. Is like, yeah, try to even focus more in linear algebra, try to explore the benefit for the even materials. If you want, let me try to do this kind of length. Oh, yeah, a long answer. Well, we had in IBM this quantum learning platform. You just it's open when you had this account. Probably all of you had access to this one. Use this funded foundations topics, you can start to understand what is the things you need to do for learning quantum computing and focus specific for Qiskit. So this is a really good chance to start what is the things you need to do in working in IBM Quantum and try to explore these different topics, because if you don't know what how can I start it, I think this is a really good exercise just to do a beginner and friendly introduction. Commonly a part of that one, if you try to do other things and you say, okay, this is easy for me, and try to explore more next topics, well, exists other things we are doing, like the Qiskit YouTube channel. We can explore different things we can do it. Exists the Qiskit Global Summer School, when we call in every year this the benefits, and even all of these videos right now of this year is right now in the Qiskit YouTube channel. You want to take a look, and even if you feel more confident with your skills about Qiskit, you can even take the certification for this one. And the next step is like the Qiskit Advocate program, when we collect this community after you finish one of these course for the for the quantum learning platform. You can, if you got this access, or when you complete one of these, you take the badge, you can participate with this program, and you can still working even with a mentor. We started this week the Qiskit Advocate Mentorship Program. When you're working with an expert for Navian Quantum, a specific problem, we got it right now in Navian Quantum, and explore the benefits about that one, or even you, like a mentee, proposal a specific project. So I try to do this more long answer. I think it's benefit for all of these people who are trying to increase in this specific area and you don't know how can I start it. Like, well, with this Qiskit Global Summer School, this is kind of old because in this year we had 8,000 people for the 2025, and we create different videos about how to the optimization, the chemistry, as a general way for the machine learning things, how we do the transpilation, how working in the hardware. Like you guys, we had a lot of people organize the Qiskit Fall Phase, so we need to say thank you so much, even if you are working in this event, because it's very important for us to spread the word, spread the benefit about avian quantum, not necessarily just because it's part of the thing we are doing. I think it's important because it's part of the future, and I think all of you people attending, participate, listen us, and take this time to learn about more quantum computing is valuable for us. Because other thing we try to do in Navian Quantum exists the Quantum Summer Internship Program is open right now. These new roles, if you feel more confident or you want to see, well, how you can be more involved in quantum computing or what is the goal, you can find in IBM careers these different roles and see what is the prerequisites or the characteristics you need to obtain in your skills in developer. Try to do these different roles. It could be in hardware, research, developer things, and it doesn't matter. We are people for different countries and working in international specific thing, and it's for different continents. The difference associated, not necessarily in America, could be in Europe, Africa, South Africa, I think so, and Asia. Yeah, like just to mention, if you're interested for the certification, where we are previously had the first certification with the version 02, and right now we had open the last couple of weeks for the new version for Qiskit in version 2. So yeah, my recommendation is try to use basically all of these benefits, because you can learn for other people to do it like an advocate. Try to learn for the previous results we're doing for summer school or the YouTube channels, and if you feel more confident, you could be even a certification. You can specify for a specific area, use this kind of activities. You can understand more what is the thing we're doing right now, like a company and a community in a general way, and you can take a look what are we doing and we can expect when we work with us, or we can expect in a company related to quantum computing. So I think this kind of resource is valuable if you are want to start in a quantum computing, you have to do like quantum machine learning or quantum optimization. Well, if you know about this one and you think it's kind of easy, because you are doing a good progress. So next step is like apply in a internship with us, for example, and try to do it. Your skill is really good. And the other the ways is like important linear algebra, part of the basic things about quantum mechanics and programming. And we are focused on Python and Rust. If you are more for developer team, but you're more focused on research. Those linear algebra, quantum mechanics, probability, programming part, and think more in a different point of view, not necessarily a classical way. It's necessarily the classical, yeah, but thinking in quantum is always good and help to think different areas, because right now in quantum computing we don't have a specific workflow or a path line for a specific problem. We had a specific general way, but we explore many ways. So it's a good moment if you had a really cool idea. Yeah, it's always fascinating for us.
Thank you very much for all your answers. It is noted, and I guess we have all benefited immensely from the presentation. I want to give a poser to you. This is much more direct because one of my collaborators, a mathematical physicist, mentioned something to me which has left me wondering. He said, uh, with quantum computing, that you can determine your answer without doing the workings, and that is why he's not truly believing in it. So I want to pose it to you from your experience.
Mhm.
Is this true? And if it is not true, I mean, as we are trying to generate this new result and directions, what are those things that you see that can pose such difficulty that the quantum computer would solve without knowing an initial state or value, or knowing the answer beforehand? Is the
Mm,
question clear?
more or less, can you explain a little more?
Okay. Yes, the professor told me that in quantum computing, one can predict the answer before solving the problem.
Okay, not really. The thing is like if we design, for example, like the oracle, just one example, is like we don't know the answer. We just know certain properties or certain characteristics. It's like how can I tell you how are you if I never see you before? I can tell you what is the thing you are wearing, for example, and try to reduce for all the spectrum information we got in this conversation, try to investigate this one. It could be true, it could be not true. So we just suppose it's like I suppose certain things is benefit for me for the solution. For example, I want to identify what is an optimal solution for a specific routine, and I don't know what is the thing, but I realize the interesting thing is doing for certain specific characteristics. So I to increase these characteristics, or depends on these characteristics, increase the probability. It will be one example. The other thing is like optimize the minimum energy depends on this pattern for a specific graph. For instance, something is like what is the minimum energy means is what is the optimal solution. In that case is we don't know, we just follow one model, we translate it in a graph, and that graph depends on the minimal energy, we can identify what is the correct answer. So it's not you need to know what is the answer. Is you know what is the properties, what is the limitation in the characteristics for any problem. It's like common problem in mathematics. It's like you know the limitation, the constraints, the variables, but you don't know the answer. Just depends of this one, you can increase the probability for that specific possible answer you can expect. Instead of using, oh, is this one? It's like, no. Probably is this one with 70%, the other it could be like 30 or 25%, the other or the rest of them is close to zero, because that means it's no interest for us. So the quantum computing no difference is like we increase probability, but it's possible or complete all the characteristics you design in your quantum circuit. But it's like probably or with a high probability could be those solution or that solution. The other is no, no, no. Don't put too much attention on all of them because probably it's not good. That is the difference in a quantum computer and a classical. It's more like, and it's kind of tricky, right? Because it's like you can expect like four, 2 by 2 is equal to 4, but it's like well, that is easy, but what happened we're doing in a parallel multiple condition or multiple probabilities objects and say, well, we had this all of inputs and probably the multiplication with 2 is probably, I don't know, for example, 175 with high probability because all the inputs you are doing assume this value. Or we can call it like yeah, that is the way. It's like one example is the subset sum problem when we had different one specific array, different inputs, and what is the subset is equal for say 7, with 1, 2, 3, 4, 5. So all of this one we can it could be 5 plus 2, 4 plus 3, 5 plus 1 is not. So we increase the probability, all of them. So we don't expect one answer. We increase every two inputs and put what is the most important translated with the high probability. And I say, okay, take a look all of this one because that could be the correct answers. The other them, it doesn't matter. That is the thing or the difference with a quantum computer with a classical. We don't expect one answer. We associate a probability. Well, we can translate is take a look with those high probability because that could be the good answer.
Okay, could that be the reason why the gates, or can I say, are the gates more efficient than themselves? For example, you mentioned for the X gate, it gives us an 100% probability. For the Adamat gate, it gives us a 50% probability. So does it mean that what you just explained now, the gates would be a determinant in achieving the results?
Uh, we don't know right now. I think it could be great try to determine it, but it's like depends on the techniques, depends on the characteristics, depends on the hardware, depends on the problem we try to do it. That is the thing is like valuable to working in this kind of areas because it's like I can tell you it could be good answer one specific hardware, one specific problem, increase 1 qubit and change many things. So it's like okay, that is a common answer when we try to do a small project. Like okay, that's good but happy with other one. But we never consider hardware. So that question is really good because it's like we never considered that one. When I do it, it's like okay, this is another project and another thing, and we need to focus in that. So yeah, that is a really good question, and the answer for me is like depends on the problem, depends on the situation. But I think that's the part we need people with this kind of ideas because we can explore that area and we can plan what is the limitation or generalize something. But yeah, that is a really good question.
Thank you very much. Thank you.
But yeah, so it was happy to me this kind of talks and always this kind of questions. I hopefully help to other student assistant because I think try to do this event is always difficult to connect with people. But for my side, I organize this kind of event. I was internship. I did this one, and now an IBMer. So I'm so happy. People still working in Qiskit Fall Fest, even if 5, 10 people listen us. But I think it's important because this area for me changed my life, and now I try to change more lives in the side with the work and this kind of talks because I think this is the future and it's difficult. We need to be honest. This area is difficult and we can spend a lot of time just focusing quantum circuit or the what is the two cubic case properties fidelity. We can spend a lot of time because it's a difficult topic, but that is not impossible to say we can work with this one. And it doesn't matter what is the country you are. So my goal of this one is like if we're listening, try to do this all these things we're doing in Avian Quantum, and try to do it. I did that one. I was a Qiskit internship. What is the other summer school? So I participated in everything. And now right now I'm a IBMer. So don't take shy or don't feel bad that you start doing. Is more practice and start to do it. So yeah, thank you so much for the invitation, and thank you so much for listening.
Thank you too.
Yeah, thank you, Alberto, for the talk. It was a very nice one and a great one. So I would like to ask a question if you permit me.
Yeah.
Okay. So I want to ask precisely what advice would you give to us because we have like a number of participants in our school. That's the in the University of Ibadan in Nigeria. So we're trying to get people to be more interested and more active. And
Mhm.
then we also push for recognition and then to help people see that this field is being represented. But then the challenge really is that quantum computing for us in Nigeria and the Africa is not even being taught in any of the university. But I know of two universities in Nigeria that they have like maybe one professor or two that is maybe taking some hardware courses, especially in superconducting qubit. So
Mhm.
then the question then will be what area for our students who are not really exposed to maybe quantum computing from the undergraduate level or the master's level, but then they are looking for a future career in quantum computing. So what would be your advice for people like this?
Okay, my personal suspect is like, how can I say? It doesn't matter if you got. I think you're doing a good job because you create this event to connect with other people. I think just to find IBM Quantum to do a talk, I think it's a good recognition. But the problem is like this is our side, it's part of our job for say something. I think the other problem is like we had a lot of opportunities. We had many things online. So exist communities like Qiskit Advocates, another will do one, and you can find other communities that one. I think the most important thing is that what you're doing. Even if you're starting with these other people, you create your community and try to keep working in that one. Just don't do it one step and yeah, continue waiting for the next year. And try to do other things, the challenge, the summer school, be more involved. And the other thing I realize is even with this kind of community, don't be shy and don't say, "Oh, the people they spare probably they know more than me." That could be true, could be no, but ask question. Or what? Even you consider this a silly or basic question, you can do it because the funny thing about quantum computing, one person takes to be one talk about quantum computing, like the mathematician guy. They had a certain point of view, but what happened with the computer science people? What happened with a physics people or an engineer? All of them has different point of view. So when you realize they had different point of view for the same specific question, it's like probably I was not wrong. So it's maybe my point of view is good, but I was focused on a specific thing. But if you be shy and you never speak with another person, how you do to say you are in a correct way? I think that is the thing is like, not be shy. Try to participate in all activities you can offer in ABN Quantum, in ABN, or even explore other in other communities. But try to speak, try to learn the new tools because you can find certain patterns in the notebooks, in the challenge, and you're always thinking why. It's not because easy, it's because it's important. And when it's important is you can understand more about the topic. So my advice is not be shy, try to participate in everything, make questions, try to do the community. I'm very involved. I'm from Mexico, so in my country it was no necessary person interested in quantum computing. Even my adversary was not necessarily interested in quantum computing. So I will start to do that one and try to do moving more myself with other students, even in other countries, and try to increase for me the confidence to say, oh, probably I'm not wrong. Probably I was not confident with me when I started in quantum computing. So I participated on hackathon, challenge, everything it was possible. For example, to say something, before that one, I was not wearing glasses, so I spent a lot of time in my computer, and right now I'm wearing glasses. So it's like, yeah, one consequence, but I think the result is a good one. So my advice it could be simple, but sometimes it's not simple because the people don't put attention in that things. So to be honest, I need to say try to do this kind of activities is good because you can do more things. You can explore your area, your career. About to say, yeah, quantum computing is complicated, but exist more things, exist more people, and internet is always useful tool to connect with this kind of people to have the good answer and the benefits, organization, communities, and explore many things. And sometimes it's oh well, and the other things it's free. Like organize a fast fail. It's like yeah, support for IBM. They spend a lot of time to get us how to do that one. I think it's a good deal. So if it's free, it's interesting for you, take it. Even if you don't have time, well, always a PhD you never had time, so you can do it.
All right, thank you. And then one last question. Would you be so kind that you share your slides with us? And then
I think
would that be possible?
no, I think it's not possible because it's more for us and IBM Quantum to share that one.
Oh, okay. Okay. Then how accessible are you in case, I don't know, if maybe some of our members may want to communicate with you directly? Is this possible or
Yeah,
it is
yeah.
not?
I use LinkedIn. Let me share you. It's just my full name,
Oh,
but
okay.
just I put in the chat just in case. In some. Oh well, I think just I put two direct message, but uh, just is my full name. You know, or
Yeah.
someone's. You can share in the chat. But yeah, I'm happy to connect with any person who has question or interest in related with quantum computing.
All right. Okay. So thank you once again very much. And maybe I can ask some of our participants to turn on their videos. Probably we could take like some good pictures.
Yeah, that could be nice. Yeah, let me know. And yeah, thank you so much for the invitation. And it was happy to do this talk for all of you. So I'm feel happy to do that one. So thank you again, and see
Yeah.
everyone.
Yeah. All right. Thank you, everyone. I think our speaker has left. And so I would like to again encourage us for this event. Like our speaker said, that we should keep ourselves motivated for the event and then also to participate more in the quantum computing learning. I'm going to be talking about this in our next talk and the lab session, just that we have the platform where we want to encourage people to keep studying and keep learning quantum computing. And it is good that our club is being recognized. Like we could see the speaker sharing our event from last year. So it means that our name is being recognized. And then as we keep being recognized, our members also will be recognized. And then when they hear, oh, this person is from University of Ibadan Quantum Computing Club, then it gives us a good recognition. So I want to say thank you to everyone and thank you for joining today.